Morning, slicing, and the floor is yours.
Great, thanks. I don't know if anyone is online because I don't have the microphone thing, but maybe I can turn this thing on and they will hear me. Anyway, I'll push the button. Okay. Well, for those here in the room, it will not be a problem, but okay. So, the essentials of tensor mining, special title, I admit. I shall start by saying that this is a joint work with Tim Seinave, with Vannieuwenhoven, both of whom are here, and also in a different joint work with also with Tim and with David Torstensen, displayed on the right. As you can see, so in case there are complaints about the terminology, you can also deflect some of it to the other two guys here. Great. So, outline for today, I'll give some introduction as to how we got to this tensor mining business, and then some additional information that we will walk through. So maybe let's get started.
If you want, otherwise.
I think it's fine. It's just maybe for the people online. Okay, it's okay. I'll continue like this.
Yes.
Oh, lights. So how the story began? Well, it actually began at a different conference, a very nice conference, which was held in the Rocky Mountains. We were isolated on the top of some mountain at this Tensors Algebra Geometry Applications conference. And at this conference, there was a very interesting talk with a very interesting name and a very interesting abstract. So you can see it over here was a talk by Martin Kasabov, and I think the title was something like, sometimes row-reducing bus tables can be useful. To be clear, this was a conference about mathematics, right? So it was a bit strange to have this title. And then the abstract is also super interesting. So they say that they will describe some type of nonsensical algorithm, which looks like it was generated by Gen AI, containing a bunch of steps that somehow appear logical, but then are composed to make something that will somehow reveal, I think he calls it structure or simplify your tensor. Okay. Fortunately, then there was also an explanation of what they did naturally. What I will tell you is based on the preprint that they have produced. So it was a joint work with Peter Brooksbank and James Wilson. And so what they described was, suppose that someone gives you a tensor in coordinates. So think of this as a block of numbers shown over there in red with some, there may look to be some structure over there, but it's maybe not entirely apparent what is this structure. And the idea that they propose is a very standard idea in mathematics. Let's say you want to find structure on some object. Why not look at the transformations of this object that would leave the object invariant? And then somehow those transformations should tell you something about the structure of your object itself. Okay, so let's look at the symmetries of our tensor. This is what they propose. And then they say, okay, well, in tensor land, one very obvious choice would be to look at the stabilizer under a very natural group action. Namely, you can act with invertible maps on each of the sides of your tensor, right? So your tensor lives in a tensor product of vector spaces. In each of those spaces, you could perform some linear transformation. And this seems like the most natural action to look for. So you could say, well, let's look at the stabilizer of this thing, but then Brooksbank, Kasabov, and Wilson observed that, okay, this would be super nice to study. However, it might be difficult to fully understand the stabilizer of some given tensor under this action. Maybe this is a bit too wild. Let's try to simplify things essentially by linearization. So rather than looking at the stabilizer itself, let's look at infinitesimal stabilization. Let's look at the differential of the equation that we have there. So the phi stabilizes A. So let's look instead at the derivative. Okay, so essentially exploit the Lie group Lie algebra correspondence to transfer the question to a Lie algebra question. Okay, and so here you can see if you have this natural action map, so you take this tensor product of the linear maps and you apply it to A. If you take the differential at the identity element over here of this phi A map, and you evaluate it again in x1, xd, so these are different x1s, xd's, but okay, for simplicity, I chose the same letters. Then what you will get is just act with x1 on the first vector space plus act with x2 on the second vector space, x. Okay? And then the idea is, okay, if you want to infinitesimally stabilize this, you would have to look at the kernel of this linear map, all right? Because the right-hand side in the equation was constant. Okay, that's great. And this is probably where Kasabov is referring to the fact, we're doing some seemingly random steps and just throwing them together. Because let's say you find this infinitesimal stabilizer, you find the elements in this kernel. So now you have a bunch of linear maps that can act on your tensor and that wouldn't move it locally. What do we do with this? Well, then you could say, well, I have a bunch of linear maps, endomorphisms on some space. How do I find structure in endomorphisms? I would look at an eigen decomposition. I would try to find the invariant subspaces and see how my map acts on the restriction to those eigenspaces. And so they say, okay, let's do that. Let's compute this eigen decomposition and then re-express my tensor in this eigenbasis. Because remember, you had basically your tensor given in an arbitrary basis in coordinates, and now you will transfer it into the eigenspace, in the eigenbases, and hopefully this will reveal some of this invariant structure in your tensor. And this is then where their algorithm popped up. So they did not give all the details at the precise presentation at the conference. They just gave the algorithm at that point. And so the algorithm is very simple. 3 steps. First step is, okay, compute some generic element in the kernel of the linear map that you see displayed over there in the first step. Second step, compute the eigen decomposition, and let's assume that it is indeed that these are diagonalizable matrices. Let's assume that this is true. And then third step, just re-express your tensor in these eigenbases, and then magically structure will appear under suitable hypotheses, evidently. Okay, so here's then some pictures that they showed at the conference. So imagine on the left side, you should imagine 4 different tensors, but if you would display them in an arbitrary basis, they would all just look like the one displayed over there. And then you run this algorithm. Of course, these are structured tensors, right? These are not generic arbitrary tensors. These are tensors with some hidden structure. You run this algorithm, and what you can find are pictures as shown on the right side. So on the right side, you see 4 instances of running this algorithm on tensors with different structure, and you would view this type of thing. So it finds this type of hypersurface, this type of curve, this type of blocking, and another surface. Yes.
So is it correct that we're only looking at abelian Lie groups? Because you would expect that there's different generators.
We're
neutral each other.
So we're just looking at GL, so the general linear group acting on the whole thing.
Okay, but we're only looking at one specific
element. Yes.
It doesn't matter, right? Because like if you pick a generic element, let's suppose that the stabilizer is reductive or nice enough. If you pick a generic element that lives in a torus.
Sure, but if there would be like non-computing elements that are also stabilizing this, there would be a much better way of doing it than just itemizing it.
Yeah, but like they should pick one. Like you just pick a maximal torus in there, you diagonalize that, and you hope for the best.
We hope for the best. All right. So these are some of the structures that you can find with this method. Of course, assuming that this structure was there in the first place, right? If you take a generic tensor, you run this method, you're not going to find by magic a full sparsification of your tensor. So they refer to this as a sparsifying method. because as it's shown in the pictures, everything that is not red is a numerical zero value. Okay, so in a way, it is revealing your invariant structure because you have zeros over there. Okay, so these are the type of things that you can find. This is what they show at the conference, and then later in their preprint, which was not yet available at that time, they describe, okay, what does this algorithm actually find? So they have a theorem about this, which is shown over here. So what they say is, okay, suppose you have this tensor A, and suppose you take some element from the kernel of this linear map. Let's say x1 up to xd. And let's assume that each xi is diagonalizable and that it has this eigen decomposition shown in the first line on the slide. So with the eigenvalues lambda I1 up to lambda I ki. Sorry for the heavy notation. Okay, and then what they show is, well, so basically in each of these maps, you have an eigen decomposition. Choose one of these eigenspaces for each of these maps. Okay, tensor up these guys. This is some vector space, and then look at your tensor at that vector space. So the restriction of your tensor to this particular subspace, and then they say, well, this restriction of this tensor has to be equal to 0 if the sum of the corresponding eigenvalues is not equal to 0. Okay. Now, why is this true? I include the proof because the proof is very simple, actually. So what's the idea of this method? Okay, so the idea is shown over here. We have a big tensor product of vector spaces, and each of these vector spaces has some eigen decomposition as determined by this element x1 up to xd that was in the kernel of this big linear map. Okay, so what happens then is that my full space of tensors decomposes as a direct sum of all these tensor products of the eigenspaces in all possible combinations. So shown on top over there. This implies then that my tensor A itself can also be expressed as some linear combination of tensors, each of which living in the particular tensor product of eigenspaces. And then we say, okay, good. So what do we have? Well, we have on the one hand that if I apply this delta map to my linear maps x1 up to xd, because these guys were in the kernel, it evaluates to 0. So that's the left-hand side in the equation. And then we can say, okay, but we can also apply the definition of my delta A map. So what's the definition of my delta A map? This was this thing over here. Just f with xj on your tensor A in the j vector space. And then you observe this tensor product of linear maps is a linear map. So if I would plug in some linear combination for my A, all this linear combination pulls out. So that's the second equation that you see over there. And then something interesting happens because now this tensor A, I, blah, blah, it lives in this tensor product of these specific eigenspaces. So if then I act with X on this guy, what happens? Well, it's just going to pick up the particular eigenspace and it will scale it over there. And that's everything that happens. So I will get a scaled version of my tensor AI, blah, blah, blah. Okay, this happens in each of the directions. All right, we have this sum over the J over here. So you get this sum over. And this is exactly what the theorem said. I have 0 is some direct sum of these scaled AIs. So each of these components must be equal to 0. So either the sum of these guys is 0 or this guy is 0. So if this guy is not 0, then the block must be 0. Okay, so this also implies if you have in each of the factors you have an eigen decomposition with multiple eigenvalues, you must have some zeros in your tensor somewhere. And this is okay. This is their theorem. This is what they say. What may happen to your tensor? Okay, great. There's a very interesting aspect relating to this, namely the element that you choose in the kernel will allow you to find different structures. So what you see here is the same tensor having a certain structure, And on the left-hand side, you see what happens when you take a generic element of the form x, y, 0. So you take the 0 map in the third direction. And on the right-hand side, you see what would happen with a generic element from the kernel with different maps x, y, z. Okay, so why do you have this thing on the left? Well, the 0 map, it scales like 0 on the entire space. So it has one eigenvalue 0 on the whole space. And this means that you're not going to find any structure in this final direction. So here, of course, the third space, the third direction is in this direction, okay? And you see that no structure is found there because you just have one eigenvalue and so one full eigenspace. There's no decomposition happening, no structure is found. While if you do allow, if you would take a generic element from the kernel, you would have a non-zero z over here, which in this case apparently has 5 eigenspaces associated with it. Okay, so here you see, I think you have 5 blocks, and you see that in each of the directions you have 5 eigenspaces of different size. Great. So for me, because this is one of the pictures they showed at the conference, this I found very interesting. Because for me, the right picture, this is very interesting because this corresponds to a very specific tensor decomposition in a specific coordinate system. So if you have a block term decomposition of sufficiently small rank and you would express it in the perfect basis, it would look like that picture. So when they gave this talk, they said, okay, this is a method for finding sparse structure and so on in tensors. While I was like, oh, wait a second, this is finding a tensor decomposition. And this then led to the topic for today, namely, can you use this type of methods under some suitable conditions to find specific types of tensor decomposition? And so specifically, I would like to look at X-rank decomposition. I think we heard about this earlier. So with an X-rank decomposition, let's say you have an irreducible variety X, which is a cone. And I'm looking for an expression of, so of course, X needs to live in some ambient space, a U tensor V tensor W. And someone will give you a point in the ambient space, and you would like to decompose it as a sum of AIs, where each of the AIs lives in X, okay? For sufficiently small rank R, okay? And then the question that we have is, okay, suppose that we are in this setting. If you would give me some tensor A that has an X-rank decomposition, will the BKW algorithm or some version of this find an X-rank decomposition, yes or no? And what are the assumptions I need on X for this to work? Okay, it's a very simple algorithm. Obviously, it's only going to work in simple scenarios. But yeah, I mean, you have simple scenarios dealt with a simple method. So I think this is a good match, at least. It would be bad if we have a complicated method to deal only with simple cases. Yes? It works for identifiable tensors as well, yes. We will get to the assumptions, and Tim will talk more about this. Okay, so from my viewpoint, if you think about simple methods for dealing with simple tensor decomposition problems, and in terms of X rank, for me, the key example is like, oh, X is the Segre variety, so I want to decompose a tensor A, as shown on the slide, as a sum of tensor products of vectors. This, for me, is like the prototypical simple scenario. I know maybe in algebraic geometry you would say, oh no, Waring decomposition is simpler because it's symmetric and so on. But let's say we look at this guy is like, in my mind, ooh, this is the simplest case. That's great. The simplest type of algorithm that I know for this case are called the pencil-based methods. And what are pencil-based methods? Well, they're also very simple methods, and they have these 3 steps over there. And what do? Well, they say, okay, just take 2 generic forms on the space W. So take 2, let's say, random vectors, and contract the tensor A with these 2 vectors. So essentially, you will get 2 matrices, 2 elements in U tensor V. there are several assumptions here, including the fact that the dimension of u, v, and w, or at least u and v, should all equal the rank of this tensor. So it should all equal this R number. This can be relaxed a little bit, I know, blah, blah, not super important. Let's suppose dimension of u and v is the same. So I basically have a square R by R matrix. In fact, I have two of those guys. And then these tensor-based methods, they say, okay, compute this thing over here. So essentially, you have we're going to pretend that we get a regular matrix tensor, and I want to compute the generalized eigen decomposition of this matrix tensor. Or equivalently, in the regular case, you could do the computation that is shown over there. Take one slice, take the other slice and invert it, multiply them, and compute the eigen decomposition. It's very simple to show that this eigen decomposition will reveal, projectively at least, the vectors AI from your decomposition. Okay? So when you compute this eigen decomposition, you will get A lambda A inverse, where the columns of A are up to scale exactly those vectors AI that you're looking for. And this is very interesting because then, although this is not the usual way pencil-based methods are formulated, given the fact that U is an R-dimensional space and I have R linearly, by assumption, linearly independent vectors AI, my space UI really directly decomposes as the spans of these individual vectors. So this means that if I would restrict my tensor A to the space spanned by AI tensor everything else, I would have a representation of my ith component in this decomposition. Admittedly, perhaps not the representation that you were expecting. Maybe you were expecting me to give you the vectors AI, BI, and CI. Those can be extracted with further processing of this tensor. But I would be able to give you a bunch of arrays that would, these arrays would be rank 1 tensors just expressed in ambient form. Okay, so I have essentially solved the decomposition problem. If I'm just interested in whatever bunch of numbers sum up to A, the problem is solved. Do you want to find more structure? Okay, then we can do additional processing. Good. So in my mind, this is a very nice pencil-based methods. They work very well for very low-rank scenarios. And then there was a really nice observation that we made, namely, these pencil-based methods are related to this BKW style method. So remember, in this BKW style method, you have this linear map, you compute the kernel of this guy, and then you, so in this kernel, you find this element, you compute these eigen decompositions separately, and you apply them. Okay, now here's a proposition that we derive saying that if you have this, for tensor rank decomposition, right, you have these two slices that you contracted, and then you take this slice, you invert it with the other guy, you get this eigen decomposition A lambda A inverse. Okay, that's what a pencil-based method does. Now let's look at what the BKW algorithm would do on a special tensor. Namely, let's look at this tensor T over here, which literally is the tensor where you would take these two slices and you put them one after the other. So you have the contraction A rho 1, tensor it up again with rho 1, and add the second thing that was contracted with the rho 2, tensor it again with rho 2. Rho 1 and rho 2 are generic, so, and I assume the space is at least two-dimensional in W. So what you get here is literally like two slices. Great. Now run the BKW algorithm, and what you can show is in this kernel of that map for T, you will find something of the form X minus Y transpose 0. With a special observation that X has interesting structure, namely X is diagonalized by A to some diagonal matrix. This diagonal matrix lambda prime will in general not be this lambda, but I don't care about the lambda. I care about the eigenvectors A. Okay. So what this is saying is pencil-based methods that have been around for a very long time are in some way computing a very special element from the kernel that is studied in this BKW method. So you could argue that this BKW method is a more general technique compared to pencil-based methods. But there is something interesting about the pencil-based methods because they're not working with the full tensor. They first reduce the size of the tensor to use less slices, let's say, of this tensor, and then they extract all the necessary information from that. And this is what we propose with, I hope this is next slide. Oh yeah, but I think probably in terms of time, I should skip that. Yeah, I'm halfway. Okay, so it has a very easy proof that you can check. Let's skip this. Okay, this led us to the idea of a kind of refinement of this BKW method that we call slicing. And the idea of this slicing method is, let's try to exploit the idea of these contractions together with this idea of this adjoint kernel. I did not stress last time. So what is this adjoint kernel? I can just move back. So if you go look at this guy here, elements of this nature, x, y, and 0, is what I call the adjoint kernel, and the general ones are called universal kernel. Kind of makes sense, I guess. And so what we want to do is to exploit the adjoint kernel. So only elements of the form x, y, and 0 are interesting for us, and combine this with the idea of the contractions to get a method that we call some slicing method. Okay, so this adjoint kernel is actually isomorphic just to the kernel of this map. You're not using this last direction, so you could just look at this map over here. Just act with x in the first direction minus y in the second direction. You could also put a plus here, of course, but it looks nicer if you put a minus. Just act in the second direction and don't do anything in the third direction, which is equivalent to saying, okay, choosing the kernel element with 0 over there. Okay, this map is called an adjoint chisel in the preprint by Brooksbank, Kassabolt, and Wilson. Okay, great. So in this method that we propose, so with Tim and with Daniele, the key object that you need is essentially this C algebra Z, which is shown over there. So you act with x in the first direction, you do minus y in the second direction, and you look at this where you act with x on a row, so a contraction of your tensor A with rho, and in the second direction, so you act with y on a different tensor B, also contracted with rho. So this Z depends on rho, the contraction that you will use, and then two tensors A and B. Okay, so that's a guy. You can check that it lives over there. So it's basically two homomorphisms between two spaces: U restricted A, U restricted B, and B restricted B and BA. What's this notation that is over there on top? That's shown over here. So with the U restricted to A, what I mean is your tensor A can be expressed. So there exists a unique minimal tensor product space in which A lives. Okay, so let's say A priori lives in U tensor V tensor W, but it may also live in some smaller subspace U prime tensor V prime tensor W prime. U restricted to A means the smallest U prime that you can find where A still lives. So in particular, if you know about flattenings, you take the flattening, you take the image of the flattening in the first direction. This will be U restricted to A. Okay, and you have the similar situation for V and for W. Okay, there's an interesting observation about this Z guy. So if you would consider the diagonal, so this Z row, it has two arguments, A and B. If you consider the diagonal, so the Z row at AA, what do we get? Well, you get the kernel of this adjoint chisel, at this contracted tensor. Okay, so always at the contracted guy. Okay, this is just a notation that we use. Great. Then we need, of course, some assumptions. The first assumption is there because I need the letter C. Okay, we have a cool acronym, literally, and I need the letter C. Okay, so the first assumption is not really a limitative assumption. We're just going to assume that our tensor A lives in a concise space. If this is not true, you can always choose better vector spaces. You choose your minimum U prime, V prime, W prime, and consider the problem over there. Okay, so first assumption, conciseness, not a problem. Then we have some actual assumptions. The O assumption, orthogonality. So what we need is, if you take a sufficiently large number K and you choose a bunch of generic forms on W, so rho 1 up to rho K, and then you look at generic AI and HAs, what we want to have is at the intersection of all those algebras with the Z guy, so this Z with the particular contraction at the two guys, if you intersect all of those, it should become trivial for some sufficiently large K. Okay. Second assumption we need is L, some locality assumption, where now you would look at the diagonal. So you would try to look, okay, what happens at the diagonal? You look at the intersection again of all those guys, and you should get some, you will get some algebra over here, denoted by the ZAI. And what is this guy? Is the intersection of all these kernels and these contracted deltas. So this linear map guy. Okay. And what we need about this algebra is that it's local. So it has just a unique eigenvalue. Right? So the previous assumption says everything kind of decomposes. The next one says on the particular piece, you should just get one eigenvalue. So that's the L. And then finally the D, because everything is cold today, is a directness assumption. What we need is that if you look at the concise tensor space in the factors U and V, it should be a direct sum of the concise space for AI, A2, and AR for some generic choice of A1 up to AR. Okay, so if I choose a bunch of points on X, I should have this direct decomposition. For example, in the Segre case, if I take R rank 1 tensors and this was an R dimensional space, for generic choice, this would be fine. Okay, so these are the assumptions. Why does it work with these assumptions? Do these assumptions ever hold? And so on is something that Tim will talk about more. But in fact, you can easily see that, or relatively easily see, that for the Segre, for example, these assumptions will hold. For up to a certain rank, of course, right? So your space definitely needs to be sufficiently large, or stated differently, your rank should be sufficiently small, should be bounded by the dimension of the space U restricted A. So it has to be R dimension after making it concise by the first assumption. Okay, so then we have a proposed algorithm that we call a slicing algorithm. The idea is basically the same as in the BKW algorithm with the incorporation of these contractions. So the idea is you choose some sufficiently, so you choose generic forms, rho 1 up to rho K. The K number is some important constant that maybe Tim will talk about a little bit more. Maybe not. So this K number needs to be sufficiently large, and it depends on the variety that you're using. And then what do you do? Well, you look at the intersection of all these individual kernels of these adjoints on the contracted tensor. So you take the big tensor, you contract it to some matrices, and you look at individually these kernels, and then you intersect all of those kernels. Then you get this Z A guy over there, and then just choose a generic element in that kernel. whatever you find there, pick it. So x and y. And then we proceed as in the BKW method. Diagonalize this, assuming that it is diagonalizable. Otherwise, you could work with generalized eigenspaces. And then re-express the tensor of, let's say, in the first direction. You can use so here it's stated just with x, which suffices. So just diagonalize x, and then essentially re-express the tensor in this basis. Or equivalently, restrict your tensor to the eigenspace ui, tensor, everything else. And this again will give you a representation of the elementary sums. So this will give you points that lie on x, but you will have them in an ambient representation. So you will find them as elements in U tensor V tensor W. Okay? So it's a method just to find some representation, not perhaps the representation you were thinking of. Okay? There's a theorem then that says that this method works under these cold assumptions. So you will need to check for your variety that these cold assumptions hold. Okay? Do we have examples of when these cold assumptions hold? Well, fortunately, yes.
But
yes.
Can you say again a little bit like this range of R where
yes,
like can you say it a little bit again? Because you need conciseness,
yes,
which in a way needs high rank. Otherwise, you're not concise.
Yeah, but the conciseness is not really. You can always restrict to a concise space.
Yeah, but then you have spaces too small to the districtness or to do the direct sum. So.
Yeah, exactly. So the direct sum will give you
you need the rank. But what are the bounds? That is what I'm asking.
Yeah. So your rank needs to be small. Essentially, what you will need
is small. You say at most.
Yeah, so here you see, when you take these generic points, you should, all these spaces will have the same dimension, right? So all these restrictions of the use to a generic tensor, doesn't matter what the label is here. So then it depends on your variety. Essentially, if you take a generic point on your variety, what is the concise space that is contained in? Let's say Segre. Segre, it will be one-dimensional. So to get this direct sum here, you can have at most R summons. If you have something like
so it's like, because for second variety, this kind of means that you only have one tensor up to changing basis. So that for you apply these, right? Because you have to be a basis.
Yes.
Be of rank R and a basis in every family.
Yes.
So it's like E1 plus
plus
ER
exactly.
Up, and this is only one up to changing basis.
Yes.
And
it's
like more. If you change your X, it becomes more like. It reveals more things.
Well, depending on the X, you will get different structure. And so, for example, if you take a Grassmann, the concise space will be like D dimension if D is the order of the wedge that you take. Yeah. And so there you can only get to R, which is the ambient space divided by D. So this only works for very small ranks. Of course, it's a very simple algorithm as well. Okay. But there are some tricks that you can use. And this is exactly where we get to this tensor mining stuff. I was optimistic with my time. And I was thinking I had more time to explain about the mining. But on the other hand, there's also not that much to explain about the mining part. Okay, so in the BKW preprint, they talk about chiseling. They call their method a chiseling method. So we were thinking, well, if we have this slicing method, because we're just using slices of the tensor, we have slicing and chiseling. Sounds like all mining operations, data mining on the tensor, revealing the structure. So we are using also a final trick that we call molding, which means you take a high-order tensor and you put it into a third-order mold. So basically, you're going to flatten the tensor. Okay? So what we're claiming is, if you use these three techniques over there, so flattening a tensor from a high order to third order, secondly, using a slicing method to reveal the individual summons, and thirdly, you can use the chiseling method to reveal any additional structure on your components that you found. So the components are somehow expressed in ambient coordinates. The chiseling method works quite well to find like the more intrinsic structure on your tensor. We found empirically, stress empirically, we currently should still prove this for Chow and for Grassmann that it really does what it does in the code. But, okay. When you do these three things, it turns out that when you implement this, it works for these varieties. And we can show for Segre, for example, and Veronese, and also for Grassmann and for Chow, we can prove that indeed these cold assumptions are satisfied. Okay. So with the same algorithm, almost literally the same code, you can deal with all these cases over there, which is quite nice because previously there was not so much for the Grassmann and Chow case explicitly in the literature. All right, so some numerical stuff. You can implement this method basically by the 4 steps that you see over here. You flatten your high order tensor to a third order tensor. You make sure that the tensor is expressed concisely by doing this structure preserving STH-OSVD. Then you apply this slicing method. And finally, if you want to find the more intrinsic structure, you need to do a special purpose method for your variety. And we find that in many cases, applying the standard chiseling method will somehow find that. So you could, for example, try to use the chiseling and see what it gives you. Okay, this was implemented in Julia, and then we have some experiments. So, for example, here is the output of the code that we have, and you can see that there are indeed a bunch of steps. The first step is indeed do this structure preserving step to make it concise. Then you extract this joint eigenbasis, so you find this element in the kernel somehow using a specialized method that works quite efficiently. And then you figure out, okay, what are these invariant subspaces, and then you re-express the tensor over there. So this is where, in this case, it was for the Grassmann decomposition, so for skew symmetric rank decomposition. You find these rank 1 guys, and then, okay, we still have to find the coefficients in case you are interested really in the decomposition of A into a sum of your, in this case, Grassmann. Okay, and then you see here, okay, the results are quite, okay. So just to show, okay, the code does something before I show the plots of this. So here we have a case of a Chow decomposition. So you decompose a symmetric tensor as a sum of products of linear forms, right? And then we see for different degrees D, and we've chosen a different number of variables depending on the degree. These parameters were chosen so that it would not use more than 100 gigabytes when running this code. So here you see for a large, for a small degree, we can get relatively large number of variables, but of course this increases rapidly. And what you see in the figure over here is the relative error. So we put in a tensor with an exact Chow, numerically exact Chow decomposition of a small rank. So the rank is equal to n divided by d in the Chow case. Okay. So you see here, for example, you go up to 100 in the case of a third order with 300. For the others. So what you see here are some nice lines. Ideally, your line is over here at 10 to the minus 16. You see that we are not at 10 to the minus 16. This is unfortunate, but at least we are still relatively low. So this is promising. It's not perfect. We are hoping still to improve it. And you can see that the behavior depends a bit on the order. It appears as if the D7 case is noticeably worse than, let's say, the order 3 case. But you see the case with degree 5 is still kind of following the blue curve. So maybe it doesn't depend on the order too much. We have to investigate. So this is the error. And the timings are shown over here. So, of course, if you increase the degree the computations become quite a bit more heavy. But on the other hand, you see that for degree 3 with the 300 variables and rank 100, the method used like 25-ish seconds. So that was quite okay, I would say. Great. So this was chow. You can do also the anti-symmetric case or the skew-symmetric case. So here is a Grassmann case, and you see that the plots are actually quite similar. So also the relative error looks quite, if you go 2 slides back, looks quite similar, not a big difference between the two. And also in terms of timings, the same type of behavior seems to show up. Okay, then finally, final numerical result. There was actually a implementation of this chiseling method that I made previously for the Grassmann case. And so here you can see a comparison in the timing between the pure chiseling method, which does not use these contractions, versus the method with slicing, which uses a contraction with, in this case, so this is a third order, so a wedge 3. Here you need to use case 4. So we can show in the Grassmann case, in wedge D of Rn, whatever, you need to use D+1 slices for these cold assumptions to hold. Okay, so here we use 4 slices, and then you see that because of this and because of some other modifications to the method, that we can very, very substantially reduce the running time. Of course, it did come at a cost in terms of the numerical accuracy of the method, where you can see that the original chiseling method is more accurate. So the red line is the slicing method. It goes up a bit with rank, while the chiseling method stays the same. This is the relative forward error, by the way. So the label is wrong, it should be relative forward error. Okay, great. So I think I saw a 5-minute warning thing. Perfect. So, in conclusion, this chiseling method that was proposed by Brooksbank, Kasabov, and Wilson is a nice method for revealing some sparse structure in your tensor, or finding a more suitable basis to express your tensor in when it was given to you in arbitrary coordinates, essentially. And what we propose is a slight modification of this method, where we're using these ideas of these contractions, of this slicing, you could say, and then combining this with a kind of chiseling, with this precisely with this adjoint chisel to find the individual components. And it looks like the numerical experiments are promising, even though there should be some improvement of the numerical accuracy still compared to the original chiseling method. Okay, so thanks for the attention. And then the references are here. So we are still finalizing the work. So then in blue is displayed the most relevant work. So the preprint by Brooksbank, Kasabov, Wilson is still it's on archive and it's going somewhere. And then the work that we're working on has a provisional working title, as you can see, but we're hoping to finish it this summer, let's say. Great, thanks.
So to go back actually to my earlier question,
yes.
So if you have like a Lie algebra that is the same, you find all the full kernel, then you basically find the Lie group on which this is invariant, and then again I talked about this yesterday. I don't know what's called in mathematics, but in physics there is something that's called the Lie-Leibniz theorem, and it tells you like any symmetric tensor under this Lie group can be expressed as some part that has the Clebsch-Gordan coefficients and another part that actually has the data.
Yeah.
And what you seem to do here is only exploit part of that.
Okay.
Property. So there should be much more sparseness that you can obtain, because actually, typically, certainly in this case, that you showed when you have like this 2 and this 3, that there's this, it's not just in one kind of direction. It's not just like a one parameter family. It's a non-commuting family. There's a non-commuting Lie algebra. So like not even the algebra. And then actually these Clebsch-Gordan coefficients contain lots of information. And this is exactly what physicists have been doing since actually the 1920s.
Okay.
This is so it seems that But there's even a much bigger kind of step that there's much more sparseness that can be gained than what you present here.
But these Schleps-Gordon coefficients, if I recall correctly, is a re-expression of tensor of subspaces living in a tensor product space.
Yes, indeed. So what the Wigner-Eckert theorem proves that if I have a tensor that is invariant under, let's say, a U, tensor V, tensor W, via all these kind of things generated, then it can be expressed as a part that's a Schleps-Gordon coefficient, and it's actually a tree, so it doesn't matter how many legs you have in a tensor. It's like the tree of Schleps-Gordon coefficients, and then actually the parameters that kind of only depend on the irrep labels of the V. So basically, all the like if you have a non-Abelian group.
But this would, I think, it would lead more to like these hierarchical Tucker-like representations.
No, but it would be very, very sparse. Okay, so this
it
would be even more sparse than the ones that you because then you can say, okay, let me just forget about the tensors. Actually, all the data cannot be compressed in somehow this data that is only acting on these degrees of freedom that are the irreps of the region. You don't.
Of course, in this scenario with tensor decompositions, usually you are interested in a particular decomposition.
Yeah, but
so of course, in the BKW,
so there's a part of it that is fixed, and there's a part of it that is variable. So that if you say, look, I have Lie algebra, I have a certain representation of Lie algebra, which this is variant, you immediately know exactly what these Schleps-Gordon coefficients have to be. So you can basically extract them, and you can express this in such a way that this data is not. There's no degrees of freedom anymore. And every tensor that would be invited under exactly this symmetry would be able to express it. You would be able to express it.
Okay, maybe we should discuss it more after the talk. Well, after the next talk.
Okay, but this is not something that is common knowledge in your community.
Probably not.
The Wigner-Eckert theorem. But this is like this for everybody, and especially nuclear physics is using it.
I think maybe the issue is if you don't know beforehand what a decomposition is.
That's easy to find. That's a linear problem. So if I find the kernel, I can construct a Lie and the Lie group.
Yeah, that I agree with. But then the decomposition to irreps might be the hard part.
No,
you find the basis.
Okay, but all the groups have been classified. We know exactly what all the
right. So you need to go through like a classification.
Oh yeah, but this is not. This is all solved.
You mentioned you were flattening from a higher order tensor to an order 3 tensor.
Yeah.
For symmetric tensors, it doesn't matter what direction you're flattening, right?
Yeah.
But you're not just working with symmetric. So how are you choosing the directions that you're flattening?
Yeah, this will influence how far you can get with a rank, essentially. So there is inside of the method whose numerical results were shown, there is some optimal way of flattening applied. Essentially, you just want to get two of the directions as large as possible, and the final direction seems like you can leave it to whatever it is.
First stop, with the data structure. I guess the cubic structure is given by the chosen basis that is like orthogonal, right? Like the cubic data should in the first. So it's given by the chosen basis that is orthogonal, like the cubic.
This one. Later.
You should like read this like so what's the difference in the chosen basis in this kind of you told that if you chose the basis in a different way.
So here the four pictures are from four different tensors.
Oh, okay.
Yeah, they're not the same here. We did have this one where it was from the same tensor, but depending on the element that you choose in the kernel, you find different structure.
This I got it. I didn't get how you chose the basis for the other one. So the wave that one is given from like a basis that is.
Yeah, so here you have someone gives it to you in an arbitrary basis because they perform some measurement. And then over here, this is the representation in the eigenbasis from
all
generic.
eigenbases.
Yes, but they are from 4 different tensors with these underlying structures. They're not. They're definitely not from. Okay, the picture is in this sense a bit easily. It's not the same one, but they would all look like this if you express them in arbitrary basis. You wouldn't be able to tell which is which.
Last question, like the last plot that you showed,
Yes.
how you take, like you put the rank and the error, relative error.
This one.
And on how many trials? Like it's just one.
This is from one trial. Just one trial for each of the. So it could be that okay, these could all be the worst case behavior that ever happened, or we could be lucky. You see it also on the red one over there. Right? We have one of these guys that is looks higher than what happened with a larger rank later. So probably this one was a bit unlucky. Maybe the next one was a bit lucky. Yeah. These we should still carry out, but we have some work to do.
No.
We enter this again.
Yes.
Use a different one.